welcome everybody to this video in our course on process control and optimization. And we are still talking about mechanistic modeling and how we can use it to model models which we then could use to design control loops. And now we want to look into an example regarding the level control we have here at hand. So our modeling objective would then be the level control. And if we look into our modeling procedure, the first thing we have to do is define balance volumes and system boundaries. And we already did this in the video before. So we defined this volume for the liquid in the system. So this is already a variable to us. The next step would then be to define the characterizing variables. And I denote this by 2. And here we have, first of all, our states, which might be relevant. And in this example, this would be then the level. The second characterizing variables are the inputs. And for this system, if we assume we want to control the level with the help of this valve, this could be like the positioning of the stamp within the valve, which we denote as S. And we have some disturbances to the system which go into, which are Vin1 and Vin2. And outputs would then be, in the end, for this control application, the measured level in the system. So now, if we look again into our modeling procedure, the first step we have, or we are suggested to do by the procedures, look into the balance equations. And the relevant balance equation for modeling the level is the mass balance. And this would denote as the change of the mass in the system. And this depends on what is flowing in by fluid 1 and flowing in by fluid 2 minus what's going out and not out through this stream. Afterwards, then we look into the next class, and this would be the transfer rates. And in these transfer rates, we also specify how these flows relate to our inputs and outputs we specify. So that means the mass flow which is going in is equal to the density of the ingoing fluid flow 1 times the volume flow 1. The same is true for the second flow and the same is also true for the output flow. So very, very simple equations. After we dealt with the transfer rates, we might have a look into the property specifications. So that's 5. And for the property specifications, we might first of all say, okay, the mass in the system is the equality of my density times my volume in the system actually. And then we might also have this assumption that the density in the system is constant since the solvent is in excess, and maybe it's also not dependent on the temperature, or the temperature is almost constant. So there are different reasons why you could assume that. And then you could maybe also say, for simplicity reasons or because of this, you are using a solvent, that all the densities actually are equal. So this is about the property specifications, and then we have the balance volume relation specifications. This was the thing where we talked about a relation. We have a bigger volume and we have different balance volumes in the system. But in the end, this is not relevant for this modeling right now. The next step then would be to talk about the equipment and control constraints, which is then 6. And here again, we have multiple things we can consider. First of all, the relationship between the volume and the level, actually, this level as a state, and maybe also the level that is the measurement signal. First of all, we could say, okay, the volume relates to the cross-sectional area of the reactor times the level. Then we could say that the level relates directly, clearly, to what is measured as the level and goes out on that arrow here. And then the second thing we might consider is the behavior of that valve. And this is described by a valve equation, and this could be denoted as V dot out equals the position of the valve, or like the state of the valve. So again, this is like closing or opening the way where the stream can go through. This is denoted by S times the valve constant, which says at a certain state of the valve there is that big a stream through the valve, and this depends on the square root of the pressure difference over the valve from one side to the other, divided by a reference pressure they use to measure this valve constant, times and reference density divided by the actual density at the valve. So, and now there's still the question, okay, what is actually this pressure difference? And if we assume this is an end which goes to the environment or the atmospheric area, and we also assume this is an open tank, we could say that the main pressure difference results from the hydrostatic pressure in the system, which then would mean that we have a delta P of P infinity, which is the environment pressure, so it's here and it's also over the on the liquid, plus our hydrostatic pressure, which is density times acceleration times level, minus our environment pressure, which is P infinity. So now we have all the equations on our board to actually combine these together and come up with our model equation, which relates actually our control input S to the level we want to control, which is L. So, and yeah, first of all, we might take our balance equation and say we plug in these relations to the volume and also to the volume flows. So this would look like the following. We have the differential of the density times the volume divided by the differential of time. And this is equal to, the mass flow going in terms of, or denoted in terms of a volume flow plus rho in 2 minus what is going out, density out times volume flow out. Very simple. And now one important step is that we say the density was assumed to be constant. So therefore, this here, the density times the volume, the derivative of time of that is equal to the density times the derivative of the volume of time. So and this is true with rho equals constant. Now, after that step, you could think of plugging this into the equation, and you clearly see, since we said all the densities are equal, all of the densities diminish. So this means then we have dv dt equals what is going in and this is true with our assumption that all the densities are equal. And finally, then you can look into the other equations and say, okay, I plug in also the relationship between the volume and the level. I plug in also our relationship for the output volume flow, which is depending on this valve equation and also this pressure difference. And then you could come up with the following final equation, which is the differential over time of the level divided, and this is equal 1 divided by the area, my input volume flows, which are disturbing my control, minus what I actually be capable of controlling, which is this valve, times, and here we have a little step, so you can like cross out the P infinity and then put it into this equation, and then you get a part with this constant, which is this reference density times G divided by the reference pressure they used when they measured times the square root of the level. And by that way, you get a differential equation which relates your control input for the valve to the state you want to control. You also have in there the disturbances, and this will help you to study this control loop and also to design the control loop. So thanks for watching, and I see you in the next video.